Today, we dive into three groundbreaking AI developments reshaping neural networks, memory management, and EEG data modeling. From Sakana AI's biologically inspired learning techniques to Google's revolutionary memory agent and Zyphra's EEG advancements, we'll explore innovations paving the way for the future of AI. AI research often focuses on optimizing existing models. Sakana AI has made a leap by moving away from conventional techniques like backpropagation. Their new method, error diffusion, ED, trains neural networks by allowing global error routing without the need for backpropagation. This approach respects Dale's principle, prevalent in biological neural networks, where each neuron's synapses are either totally excitatory or inhibitory. The beauty of Sakana AI's dual-stream networks lies in their architecture. These networks are divided into excitatory and inhibitory components. This design aligns with how biological brains operate, using task-dependent credit assignment. This means that the model efficiently decides how much each task influences learning, increasing the system's adaptability. Error diffusion addresses a critical limitation in traditional neural network training. Backpropagation, while effective, is computationally intensive and not always biologically plausible. By foregoing backpropagation, Sakana AI's method promises energy-efficient training, potentially reducing computational costs in large-scale deployments. This is particularly beneficial as AI systems scale up and demand more resources. The implementation of modulo error routing enhances the versatility of ED, allowing it to tackle more than just binary classification tasks. As a result, Sakana AI achieved impressive accuracy of 96.7% on the MNIST dataset and 61.7% on CIFAR-10, demonstrating the viability of biologically inspired techniques. This highlights a critical benchmark where ED not only stands out in efficiency, but also in performance, challenging existing paradigms. Nonetheless, there are trade-offs and limitations. Scalability with more complex datasets remains a significant concern. The generalizability of ED outside its tested conditions is still under observation. Comparative studies with backpropagation under various conditions are necessary to fully evaluate its potential. Moreover, as task complexity increases, ED might encounter bottlenecks that limit its performance. For those interested in exploring this further, the research paper, Diffusing Blame, Task-Dependent Credit Assignment in Biologically Plausible Dual-Stream Networks, offers detailed methodologies. Practical implementations are available on platforms like GitHub or Hugging Face, where enthusiasts can reproduce results using MNIST or CIFAR-10 datasets. The implications of ED stretch beyond a single innovation. It represents a shift towards training methodologies that resonate more closely with biological processes, promising more robust, adaptive AI systems. These systems not only enhance performance, but also potentially offer sustainability in AI development, making them a compelling area for future research and development. Breaking free from traditional retrieval methods, Google Cloud's always-on memory agent is changing how AI models manage memory. By moving away from retrieval-augmented generation, RAG, and embeddings, this agent allows continuous memory consolidation, significantly enhancing the efficiency of applications that require persistent contextual understanding. Technical aspects and integration. The always-on memory agent integrates seamlessly with Gemini 3.1 Flash-Lite, Google's most recent model tailored for demanding developer workloads. With its continuous memory management capability, this agent optimizes AI interactions with previously encountered inputs, providing a more fluid and adaptable user experience. This continuous consolidation feature not only reduces the need for repeated data retrieval, but also allows for faster access and improved accuracy in understanding and response generation. Gemini 3.1 Flash-Lite marks an improvement over its predecessor, the Gemini 2.5 Flash, particularly in speed and cost efficiency. It slashes operational costs to 25 cents per million input tokens and $1.50 per million output tokens, offering substantial savings for businesses with high-volume AI needs. Additionally, the time to the first answer token is reduced by 2.5 times, while the overall speed of output generation has seen a 45% increase without compromising quality. Performance and benchmarks. Gemini 3.1 Flash-Lite has achieved an impressive ELO score of 432 on the Arena.ai leaderboard, outperforming previous models in reasoning and multimodal understanding benchmarks. This positions the model as a leader in AI performance, underscoring Google's commitment to advancing the capabilities of memory optimization. Practical considerations and challenges. Despite these advancements, deploying the always-on memory agent requires consideration of resource demands. Continuous memory management can be resource-intensive, particularly for complex tasks where contextual memory depth is crucial. Businesses must weigh the benefits of speed against potential trade-offs in quality and resource utilization. Moreover, the reliance on continuous memory consolidation poses risks of memory accuracy degradation, as excessive dependence might lead to a narrowing of contextual coverage, influencing long-term AI reliability. The challenge lies in balancing memory optimization with maintaining diverse and comprehensive contextual understanding. Applications and future prospects. Developers interested in leveraging these advances can explore the Gemini API for integration into existing applications or test the always-on memory agent for enhanced contextual AI responses. Resources available through Google Cloud documentation can provide additional guidance on optimizing usage in various operational contexts. As AI applications increasingly demand persistent memory capabilities, this shift in strategy reflects an era in AI where improved memory management can redefine contextual processing. This technology certainly sets a foundational stone for future innovation, promising to alter the competitive dynamics among AI model providers and enhancing developer experiences towards more efficient, context-aware models. Zyphra's release of Zuna 1.1 is a groundbreaking development in the field of EEG data modeling, offering substantial flexibility and new capabilities for neurotechnology research. This model is engineered to handle variable-length EEG inputs ranging from 0.5 to 30 seconds, licensed under the widely adopted Apache 2.0. At its core, Zuna 1.1 utilizes a diffusion autoencoder architecture, which includes an impressive 380 million parameters. This design enables the model to effectively denoise, reconstruct, and upsample EEG signals, even when presented with arbitrary electrode configurations. Such robustness allows Zuna 1.1 to adapt seamlessly to varied EEG datasets, addressing significant challenges in this domain. While specific benchmarks for reconstruction quality are still forthcoming, the model already demonstrates a noteworthy ability to manage noise and missing channels, which are common hurdles in EEG data analysis. However, it is important to note that the model's generalization capability across different EEG datasets still requires empirical testing. Moreover, the efficacy of Zuna 1.1 in handling particularly complex EEG signals hasn't been fully evaluated. This means that while the model shows promise, further validations are necessary to establish its comparative performance metrics against peers. The ease of integrating Zuna 1.1 into existing workflows is evident with its availability on prominent platforms like Hugging Face, GitHub, and Zyphra Cloud. Researchers and developers keen on exploring EEG applications can quickly get started by using the command pip install Zuna 1.1 to embed the model into their projects. This accessibility underscores the model's potential to serve as a tool for fostering innovation in EEG analysis, precisely when robust approaches are needed to advance neurotechnology and brain-computer interfaces. Zuna 1.1 stands not only as a technical achievement, but also as a beacon for future exploration and collaboration in the EEG landscape. Its open-source nature under the Apache 2.0 license encourages the community to contribute, iterate, and potentially overcome still existing limitations, paving the path for enhanced neurotechnology solutions. These advancements illustrate the continuous evolution in AI, from training methodologies inspired by biology to groundbreaking memory and EEG processing techniques. Stay curious and explore how these innovations can enhance your AI applications. Join us next time for more cutting-edge AI insights.